Welcome students. Today we will study the next application of Gauss theorem is sphere. Okay, so in sphere there are two cases. One is hollow and another one is solid. The hollow sphere is known as shell. So first case we will study is a shell. So we will draw a shell like this, and in both the case what is the area? Surface area in solid and hollow, you know it, that is 4 pi r square. So let us distribute the charge. At this is hollow, on the surface the charge will be distributed. Okay, this is the center, and let us take this radius as capital R to the surface. Now the first case I will find what should be the electric field outside. Okay, I will take a point P here, and with a distance R from the center I will find what should be the electric field at this point P. So what we have to do, the first point is enclose with a Gaussian surface, and you know it is a sphere. How you can enclose a sphere? With another sphere. So I have drawn a sphere. Okay, so now let us calculate. You will write for the flux calculation phi at this point. How will you calculate? The formula is close integration of E ds cos theta. Okay, for this small area ds, where is the electric field? Outside. Where is the area vector? Outside, because the electric field is coming like this. Electric field, okay, plus charge, electric field is going like this, plus charge, electric field like this, plus charge like this, and this is the area vector. How much angle they are making? 0 degree. So what is cos 0 degree? 1. So what you will get? Only E close integration of ds, that is E into S. And what is the surface area of a sphere? 4 pi r square. Now what is the next step? The next step is compare. With what? Compare with the Gauss equation. And what is the Gauss equation? You have to compare E into 4 pi r square with q upon epsilon naught. Okay, and what is our basic job? To find out electric field. What is electric field? Q by 4 pi r square epsilon naught, right? And what is the relation between E and small r? E is inversely proportional to r square, right? Now let us find out the second case on the surface. Okay, on the surface with a distance capital R. So nothing you have to do, already you have derived your previous equation, E equal to q by 4 pi epsilon naught r square. Just replace this small r with capital R, q by 4 pi epsilon naught r square. E increases as r is decreasing. The same case, E is inversely proportional to capital R. No need of any derivation if you have already derived the equation of this, right? Now let us find out inside of a cell. You know it very well, the cell is hollow inside, so no charge can stay inside. As no charge will stay inside, what should be your electric field? Your electric field is 0. You can write down the note by pausing the video. You know it very well. No charge inside the hollow sphere because there is no atom present inside. If no atom is present inside, then no charges will also be present. Then to which it will attract or which it will repel? Nothing to attract, nothing to repel. So your electric field inside a shell is 0. So no charge will stay inside. Now if we will study the solid sphere, then this is your solid sphere. Okay, and where should be the charge distribution? As you know very well, there are atoms inside a solid sphere, so there is a chance of repulsion or attraction or whatever it may be, so the charges will reside inside. If you give similar type of charges, what will happen? They will repel to each other and they will go to the surface. Clear? But the distribution is like this. So what is the first case? We need to find out outside of the sphere, outside of the solid sphere. We'll take a point like this with a radius small r, and we will find out what is the electric field present at this point P. So what is the first point? Enclosed with a closed surface or Gaussian surface, right? And how to enclose a sphere? By drawing a sphere. The same case is that of your hollow. And what is this to this radius? Capital R. Okay, so you will get the formula by deriving the previous equation, or if you observe the previous relation, that is hollow spheres outside concept, you will get the same formula. Let us check it out. So what you will do? Flux calculation, close integration of VDS cos theta. The same thing will happen. The same thing. If you enclose this one, here if you will find out the flux, this is the area vector and these are the electric field lines. How much degree they are making? 0 degree. So cos 0 degree equal to 1. The same thing. Cos theta equal to 1. So now E close integration of ds. So this is Es. Again for the solid sphere, you will not get the surface area different. You will get the surface area same, that is E into 4 pi r square. Now compare with the Gauss equation, that is E into 4 pi r square equal to Q by epsilon naught. Okay, and E equal to Q by 4 pi epsilon naught r square. Okay, and you will get the same relation. E is directly proportional, sorry, E is inversely proportional to r square, right? For the second case, on the surface of the solid sphere, you will get the equation, nothing to change, only change instead of small r, write capital R. Okay, you will get E equal to Q by 4 pi epsilon naught r square. As E increases, r is decreasing, right? Now let us find out what will happen if I will take a point inside a solid sphere. Okay, so I have taken a point P here at a distance small r, okay, and drawn a Gaussian surface like this, okay, and this to this is capital R. Okay, so now at point P at a distance r from center, you will find out the flux calculation. Phi equal to, what is the flux calculation formula? Phi equal to close integration of E vector dot ds vector equal to integration of E ds cos 0 degree. Why cos 0 degree? Again this is the small surface, so area vector is this, electric field lines also this, so both are in the same direction, so cos 0 degree equal to 1. So E into integration of ds, what will you get? ds integration is s. So what is the surface area of a sphere? Into 4 pi r square. Why small r square? Because here I am calculating at this point. So what is the radius? R. So this is r square. So next step is compare with the Gauss equation, that is E into 4 pi r square equal to Q by epsilon naught. Okay, compare with the Gauss formula. So now let us take, this is a sphere, so it is having some volume. So here a concept will come, volumetric charge density. So volumetric charge density is rho is equal to charge per unit volume. So what is your charge? Q equal to rho into V. So what is the volume of a sphere? 4 by 3 pi r cube into rho, right? So now let us place it this q at this point, this equation. Okay, so E equal to, directly I am writing by placing the value q, 4 by 3 pi r square into rho whole divided by epsilon naught into this 4 pi r square will go this side to the denominator. Okay, so 4 pi r square. So you will get the answer rho into r by, at the denominator you will get 3 into epsilon naught. So here you are getting E is directly proportional to r. E is directly proportional to r. Now let us draw the graph of the hollow sphere. Okay, this is what? Hollow sphere. So the graph is like this: y-axis, x-axis will take this side origin 0, side r, this point r, and this point small r, this point onwards, and this y-axis as E, electric field. So in hollow sphere you have observed up to 0 to r, this is hollow, the sphere is hollow, yes or no? So no electric field inside, yes or no? So no electric field inside means what? Up to 0 to r, up to 0 to r, what is the electric field? 0 to this, 0. Okay, so you will just make a line like this. After that, at this point r, on the surface charges are present. So what will happen? You will get the maximum value of E. What you will get? The maximum value of E. This is what? E maximum. You will get the electric field maximum. After that, when you will go outside R by enclosing some Gaussian surface, okay, outside the surface, then what will happen? It will gradually decrease, because you know the formula, E is inversely proportional to R square. Okay, so what will happen? It will gradually decrease when you will go up to R. This is the graph for hollow sphere. From where we got this equation? From here we got the equation. E is inversely proportional to R square. This is what? Outside of the cell, this derivation. Now let us draw the graph for the solid one, solid sphere. This is y-axis, this is x-axis, same, this is 0, this point is r, this is r. Okay, this point onwards r starts, and this is electric field in the y-axis. Okay, so in the solid sphere, inside what? Your charges are present. Okay, so if you go from center to this point, okay, what is the relation? E is directly proportional to R. If you increase your R, your E will also increase. If you increase your R, what will increase? Your electric field also will increase. Okay, so when you will reach to your capital R, what will you get? You will get the, this is R, yes or no? This to this is what? R. So if you will go to your R, what will you get? You will get your electric field as maximum. So if you increase your electric field, if you increase your radius, the electric field will also increase, because it is directly proportional. If you increase your radius, the electric field will also increase. So it will gradually increase like this, and at this R you will get the maximum value. Okay, when you go outside, okay, you know it very well. What is the outside relation? E is inversely proportional to R square, whether it is a solid, whether it is a hollow, it doesn't matter. If you go outside, okay, what is the relation between E and R? That is inversely proportional. So you will get a graph gradually decreases. Clear? Thank you.